In these next two units, we're going to work with statistics and probabilities. In Unit 6A, Lesson 1, we're going to focus on geometric probabilities. Geometric probability simply refers to the probability that a certain event is going to occur over the course of a given area of some geometric shape. So our basic equation is going to be the geometric probability is equal to the desired area of that certain event occurring divided by the total area of the given shape. Now we're going to go through a few examples of finding geometric probabilities. So find the probability that a randomly chosen point will lie in the shaded region. So we have a rectangle within a rectangle. So our basic equation we're going to use is the probability that it lies in the shaded region, that the randomly chosen point. So we'll just use P stands for the probability of S is going to represent the shaded region. That's going to be equal to the area of the shaded region. So we'll use A sub S divided by the area of the total shape, which is that larger rectangle. So A sub T, we can use T to represent the total shape. Now we need to find each of these individual areas. First, we can find the area of the total shape because that's going to be easier to calculate. The area of the total, we just have to multiply our base times our height or our length times our width. So if we take 15, whoa, that's not a 5. If we take 15 times 9, that is going to be equal to 135 square units. Now if we want to find the area of the shaded region, the area of the shaded region is going to be equal to the area of the total minus the area of the inside. We just found the total area is 135. So we take 135 minus the area of the inside, which we find by taking 3 times 9, which is 27. 135 minus 27 leaves us with 108 square units. Now we plug those values into our formula. So we have 108 divided by 135. Now if we calculate that as a decimal, that would be 0.8, which would be 80%. So if we randomly picked a point in this overall rectangle, the probability that it's going to lie in the shaded region is going to be 80%. In the second example, we want to do the same thing. We want to find the probability that a randomly selected point is going to lie in the shaded region. So we have to find the area of the shaded region divided by the area of the total. The area of the total is easy to calculate because it's just a square. So we would take 10 squared, which is equal to 100 square units. Now we need to find the area of the shaded region, which we're going to find by taking the area of the total minus the area of the inside circle. We know the area of the total is 100. And then we have to subtract from that. Now to find the area of the circle, if we know the length of one of the sides of our square is 10, that means the diameter of the circle is 10, which tells us that the radius is 5. So we're going to subtract pi times 5 squared. If you take 100 minus pi times 5 squared, you get approximately 21.46. So now we plug these values back into our equation. The area of the shaded region is approximately 21.46 square units. The area of the total is 100. So if we divide those, we get approximately 0.21, which would be 21%. If we randomly select a point in that region, the probability that it lands in the shaded region is going to be 21%. Example 3, same idea. We want to find the probability that a randomly chosen point is going to lie in the shaded region. So we have to find the area of the total shape, which is a little more difficult this time because we have a trapezoid. And then we have to find the area of the shaded region. The formula for the area of a trapezoid is 1/2 times the height times b sub 1 plus b sub 2. B sub 1 and B sub 2 stand for the bases of the trapezoid, the two sides that are parallel to each other. Plugging in our known values, we get 1/2 times the height, which is 12, times the sum of the two bases, which is 14 plus 20. We simplify that, we get 204 square units for the total area. Now to find the area of the shaded region, we take that total, which was 204 square units, minus the area of the inside unshaded region. So if we take 14 times 12, that would be 168, which leaves us with 36 square units for the shaded region. Now if we take the area of the shaded region, which we found to be 36, divided by the area of the total, which is 204, we get approximately 0.18 or 18%. Probability of randomly selecting a point that lies in the shaded region is going to be 18%. Now to the last example, finding the probability of randomly selecting a point in the shaded region. First, to find the area of the total, we have a rectangle, which is length times width, so 4 times 3 would give us 12 square units for that total area. Now to find the area of the shaded region, we have to take the total minus the area of the unshaded region, which is represented by both these circles. We can assume in this case that both circles are going to be congruent. If this length of the rectangle is 4 units and these two circles are congruent, that means the diameter of each of these circles is going to be 2 units, which implies that the radius of each circle is going to be 1 unit. So we're going to subtract 2, because we have 2 circles, times pi r squared. Pi times the radius is 1 squared. Now if we simplify, we get 12 minus 1 squared is 1. 1 times pi is just pi. So we're subtracting 2 pi, which leaves us with approximately 5.72 for the area of that shaded region. Plugging in our known values for the area of the shaded region and area of the total, we get approximately 5.72 square units divided by 12 square units, which gives us approximately 0.48 or 48%. Finding geometric probabilities isn't too confusing. You just have to take the area of the occurrence you want, the shaded region in the examples we did, divided by the total area to get that approximate value. Convert that to a percent if you want, or the decimal. You just have to remember the formulas for all of these common shapes: rectangles, squares, circles, trapezoids, so that you can apply them now to find geometric probabilities.